So can see these slides here. Can you share them on your?
Okay, sure. Um,
I think you need to do it in StreamYard.
okay.
Let me test it.
I guess I will just share my screen.
That does not.
Doesn't work.
Okay.
The browser can't access the screen.
Oh shit.
You can try to share a tab maybe.
Yeah, I think this works. Yeah. Yeah. Hello everyone. I mean, I guess you're seeing the WebAssembly, but probably might not talk about the WebAssembly part for the talk. But yeah, we're going to be speaking about like portable DSLs with NOM. And we'll briefly like discuss more about like how probably we might just briefly like touch on how you can make it like really portable. Just a brief introduction about myself. My name is Tuchkin Kendallin, but that's too long. Everybody calls me Tox, so feel free to like call me Tox. And I'm a software engineer at Lenovo also. I mainly work on the manufacturing team, building models that improve like time, costing for users who use our product, and most of it we serve like the electronics market. Um, so just to dive in, what really is like DSL? Generally, DSLs are like domain-specific languages, and they're like languages specific to a particular domain, and like sort of like allows you like programmatically perform like operations on domain-related like information or data. So to fully explain what I mean by that is Cloudflare, for example, which is going to be what we are going to be using or sort of like implementing. On Cloudflare, they have like this rules option that allows you like programmatically like set rules. Maybe you want to transform requests or responses that match certain like criteria, things like that, or Notion. If you use Notion, something like this. So these are actually like domain-specific languages that fit like the domain. Like for example, on Notion, you can query like fields specific to like a database and all of that. And why am I really like giving this talk was because Luminovo, we my team specifically, we had to implement something similar, um, which allows a B2B software allows users to be able to like query data, and then with that data that they query out, they can then calculate like the time it takes like to let's say manufacture like a PCB, or the time it takes to manufacture like an electronic component. But there are like certain filters that we needed them to be able to write, or queries that we needed them to be able to write to be able to perform this. And the beautiful part is that most of our users have zero to no programming experience. And I think that's also like important to like consider if you're going to like be building DSLs. You need to like consider users. And one of the major reasons why we didn't go with just any other like programming languages, or like probably like just embedding like the Python interpreter on our UI, was because of we had to like question like a couple of things. Who are use case? What's our use case? Who are the people who are using our product? Will it satisfy like all of our goals, all of our objectives? And so like a lot of back and forth went into us deciding how to go about it, like speaking with end users, iterating on like probably even basic things like how should the functions be like, how should you interact with it. Most of our users were used to Excel, so we needed to like also think in line with that, like how can we bring things that the way they did things like in Excel and also fit into like our own domain. And so like why would you want to like build one? You want like the flexibility, ownership for users. Like right now, users have full control of what they want to do. They can perform like complex calculations. For example, maybe query out all the electronic components that are type THT or SMTs on a PCB board. they can do all of that without having to reach out to anyone for like assistance whatsoever. And it also like allows you to like easily represent like solutions like domain problems. Like now users know that, oh, if I want to be able to maybe see how long it's going to take to manufacture this board, they can easily like programmatically represent all of those solutions. And also like freedom to like interact with like all of these domain data and so on. There are still more benefits, obviously. So considerations, like I spoke earlier, there are certain things you need to like consider. That is readability. You want to ensure that it's easy for these users to like read these things and be able to like understand exactly what it is. You also have to like factor in security, learning curve. Should it be interactive or shouldn't it be interactive? Like interactive in the sense that, or should they get like feedbacks? Should they get like intelligence and all of those things? And also like debugging and so on. Like, do you want to highlight when there's errors, when there are errors and so on? You also have to like factor in like domain entities. Domain entities are what are all the entities that are required. Like for example, let's say the Cloudflare filter. One of the things that is really important in their own domain, things like IP addresses and all of that. And so when you have those kind of domain, when you have like knowledge about like the domain, you can better like model the problem as you would want. So for example, our own use case, like the left-hand operators were like one of our use cases was like the left-hand operator obviously is just a a variable. But if you look at like that of like Cloudflare, for example, for their rules, you find out that they could do things like maybe IP address dot length. I mean, it depends on the structure of your data and depends on how your data is specific to like your domain. It shapes like how you go about it and operations to like support like what are the kind of operations you can do with this data. Is it aggregation? Is the goal to aggregate or is the goal to evaluate to like a single value or whatever the case might be? I feel like it shapes a lot of things. So now let's talk parsers. So specifically, we're going to like there are different like parsing libraries. For those who might not like be familiar, but I guess most people are familiar with parsing. Basically, you have like this source code and you basically like match it again in code like certain types of like rules or what we would call like probably like a grammar or something, grammar rules that you've already like declared, and then you arrive like at a structured kind of representation, which most of the time we often refer to as the abstract syntax tree or the AST. The different types of parsers generally, there are parsers that go after like combinators, like combinator in the sense that you build little pieces and then you combine these little pieces into one whole. And I really like this kind of parsers because it's easier to test, it's easier to build little things and then combine everything together. It's just like Lego bricks, like you build little things, you test that these little things work, and then you're sure that when you bring it into the full structure you're building, it does exactly what it's supposed to do. There are also like peg parsers, like what PES does, where you write your context-free grammar in probably like a file, and it has to like go stick with their standards and all of that, which is also good. But the reason why I don't really like them because I feel like it's overhead for other people because then you need to understand how does PES want you to write these things. But like with libraries like Norm, you're still calling it like just like your ROS functions, which you'll see. And they're also like handwritten parsers, which most of the time I feel like most programming language go this route because it allows you to like suck so like optimize things. You have that flexibility. You can do most of those things, but you can also do those things with Norm. Just speaking briefly about like Norm, I really like Norm because like it provides like the concept is like I mentioned earlier, you have little functions you can call together to perform operations on inputs, and if it fails, it recurses and tries another branch of parsing. And so like the way like Norm works, it has like these different modules that do like specific things. So there are parsers that operate on bit, there are parsers that operate on branches, there are parsers that operate on bytes, there are parsers that are combinators. You would see more examples of like that as we go on. And so for example, for the bytes, so in Norm, there are two routes most of the time, which is like the complete and the stream. So the stream allows you to do parsing like as you get the input stream. So that means even though you don't have the complete input yet, you can still be passing. Um, I haven't implemented this, but like I know like Wazim, for example, does like streamed compilation and all of those kind of things. So I mean, probably if we were to implement that, that might be a good use case. Um, but like complete, it's saying that you have the complete input and you want to pass on the complete input. And like they're useful functions, like for example, the major one we're going to be using is stag. And so you can say if you see a full stop, or if you see if you see the keyword true, you should pass it into a Boolean value true. You can do things like keep taking input until it matches a particular condition. And so these little functions are there, and then you can combine these little functions. And so why num? It's easier to test, easier to pick up, it's faster to implement. I guess also well maintained. That was like also like a huge tiebreaker for us when we're looking like at other like passing libraries. And it's native to like Rust and it's compact. So what are we going to build for this talk? We're going to be building like the stripped down version of Wireshark filters, and Cloudflare also uses it. So the user interface I showed you is the way Cloudflare like filters out all of those values, implements like their DSL. They implemented it from like Wireshark filters. It follows like that kind of spec. And so an example of that is something like this. So this is just like a stripped down example to just like get an idea of what it does. Where you can do like frame of length is greater than this, or you can say frame of time is equals to this, or you can do TCP.port is equals to this, or and so on and so forth. And you can combine more of these complex things. This is pretty easy to implement because it's like one layer deep. But like for example, our own case, it's had things like more complex types, nested structures, and all of that. So just if you like to see how the display filters, the spec is like, you can actually check it here. You can also like see, the reason why I like this is because it's kind of like really extensive and it's simple and straight to the point. So probably it's something you can decide to like implement like as a pet project. It wasn't like really hard for me to like get this up and running. Probably like you can get like this spec up and running within like probably like a day if you understand how node works, or probably even less. But yeah, the spec generally contains like integers, unsigned integers, booleans, Ethernet addresses, IP addresses, text strings, date and time. But these are the general ones, and they have like operations like combinate logical operators, comparison operators, and so on. Going for that. So data types, which I already mentioned, these are like the data types, basic primitives, like for the DSL, for Wireshark filters. And so these are like logic operators. So enough of the talk, showing the code. Yeah, so let's assume we want to. So firstly, let's build the basic functions. So in this language, the DSL we're trying to build, they are basic primitives like Boolean values. And so for Boolean values, what are we saying here? We are saying, firstly, there is the alternate tag. The alternate tag is saying try to pass with any of these parsers. So firstly, tag is a parser. This is also a parser. This is also a parser. And if you remember at the beginning, tag says match for this input. So what is happening here is try to match for this input where the true is capital letter T with the remaining in lowercase. If you try to match the input type and you see that it fails, proceed to match with capital letter uppercase through. If it fails, proceed to match with a 1. So with something like this, so the good part is if one parser fails, proceed to the next one. And if you pass it successfully, return it. We have like this type called operand, which has a variant of Boolean, which wraps a true. And so if you pass it successfully, returns a true. Same for false. Try to match on any of these inputs. If it passes successfully, return a false. And so we now have a function that says lex Boolean. And what it does is it says try to pass a true If it fails to pass it through, attempt to pass it false. Firstly, try to pass it false. If it fails, try to pass it through. And if true succeeds, return the result of the passer that succeeded. And so you might be wondering what this I result is. I result is just a type created by norm. It abstracts quite a number of things, but generally what it wraps is just a result type with SRC. SRC is the input. So SRC is the input, and it also takes in the operand, which is the return type, and there's also an error type, which isn't shown here, but unless you want to override like the error type, you would explicitly like specify it. For our own use case, we had to specify error type because we wanted to have more control about things like line numbers, give span information and all of that. But this is just a stripped down version. Use the default for every single thing. And you may be wondering what is SRC? So in NOM, there's a library called non-locate, and it's just a wrapper over a string that just the wrapper, aside from just the string, contains line numbers, the current place where it is passing, the position, and all of that information. So when I get like inputs, SRC, I basically have all those informations at that point in time. So we understand how Boolean works. Pretty much the same thing too for numbers. So for numbers, for binaries, we are saying recognize if you see the 0 and the B. So first of all, there's a preceded. Preceded is like check to see that this is the prefix. And then if we can see that 0B is the prefix, then we want to proceed to match on the input. And what is the subsequent thing after this 0B? It's saying take all characters until you encounter a digit that is not in base 2. So we're saying take all these characters, keep taking, and the requirement for you to continue taking is if it matches a digit with in base 2. And if that succeeds, we want to now map the result into this closure. And generally, what are we doing? So if it passes successfully, we take that input that was passed, the binary string, and we say, oh, we want to convert it into an I64. So that's generally what it's doing. For simplicity, all the number types are also written I64, but generally you want to have like more specific types so that you can like you can obviously like not have like values that's just wasting space generally. Same too for octadecimals, pretty much the same thing. Keep taking until you encounter a digit that is not an octadecimal, and take what you've passed successfully and convert it into an I64. Same thing too for hexadecimal, same thing too for decimals. And so you've noticed we have all these little functions, and the good part is you can test these functions. You can test it in the sense that you can just write a function, if in your test, like a function that says, hey, take in this input and check to see if it returns, if it passed only this in output. And if this is the remaining text that wasn't passed. And you can write all of these basic unit tests for each of these your functions, and you're sure that it's going to do exactly what it's meant to do. And so we have all these functions. How do we all bring it together? To now pass a number, we say, okay, try to lex a binary. If it fails, try to lex an octadecimal. If it fails, try to lex a decimal. If it fails, try to lex hex. And if that succeeds or either of them succeeds, we want to map the results into a type that we created, a variant, which is an integer, and basically it's just a wrapper. It's just like wrapping an I64 generally. Please feel free to like stop me if you have like any questions or anything you're like clear about. Same thing too for strings. Strings we're saying, so strings are wrapped in quotes, kind of very tricky. But what we're saying is there's a function provided by NOM called delimited. So this is why I really like NOM. They have like inbuilt functions that already do like specific niche things. So it's saying the way the delimited function works, parser works, is like it says take the match on the first value. If it succeeds, proceed to match on the second value. If it succeeds, proceed to match on the last value. And if all this, especially like the first and the last, so if you have like an opening quote and a closing quote, if you pass that successfully, then the result of your get string, you want to map it into a string. So the string is just still like a wrapper over like a string type of Rust generally. So the question I'm asking is, what exactly is get string? And so get string is a function that I implemented. Okay, adapted from there's also like this example like a norm called I think monkey patch or monkey. So this was already like implemented. Probably I just renamed a bunch of things to make it like more readable to me, but it's pretty much the same thing there. And generally what it does is what makes strings tricky. It's just the concept of escape characters. If not, you can just keep taking everything until you encounter like the closing quote. So what's happening is, remember we've taken the first quote, the opening quote, and so what we are saying is if we encounter a closing quote, we want to just return an empty string. If we encounter an escape character, we want to take out that escape character. That's what we're saying. Take out one character out, one byte, and then proceed to call this function recursively. So we've taken out that escape character. So we now try to get the remaining string. When we've gotten that remaining string, we concatenate it to what we had previously before we encounter the escape character. And so that's why we just call this concat string. Concat string is just a function I wrote that concatenates two strings together. It takes the escape character and the accumulated value that it passed recursively. And while for current, we're just saying get the current string without the current. That means without this current character that we encountered or the current character that we just passed. So we get subsequent ones. After we get subsequent ones, proceed to concatenate it to what we currently have. Just recursive function. So it keeps doing that, and the base case is just this last one. So once it reaches like the end, return an empty string, and I mean concatenate an empty string to what you've been passing previously. For datetime also, datetime is pretty much the same. Datetime are wrapped in strings. So we still call that a get string function, the get str function. So we get the content of the string, and then we try to pass. So if you check the spec, there are a couple of supported date formats. This is not all, but this is just like an example. So we attempt to take that string, try to pass it into a datetime. If it fails, try another format. If it succeeds, convert it into a datetime for the operand type that we created. If it fails, return back like a custom error. So remember I resolve. I mentioned that I result is just a wrapper over Rust error type, but the only thing is just that there are still like more fields that it abstracts. So this is just like an example of what is there. You might be wondering, why did I return like a regex expression matches? So by default, we're not overriding the error type that none provides out of the box. For our own case, we were using, not for this case, for what we implemented, we had like our own error type. So in cases like this, we would handle things like spam information. What should we highlight? What should we flag as an error, and so on and so forth. But for this, I just returned like a regex expression matches error. That's signifying that this failed because it failed to match the regular expression that we passed. Probably there are other error types I could have used, but I just used this. This is just pretty much basic. And so for MAC addresses, so I mean, there are better ways I could have gone around this, but like I was very limited on time. So generally, if you look at the format of how MAC addresses are, it's either you have this or this or this. I could have written like parsers that matches like in pairs of twos with either a dot or a dash in between, or matches like in pairs of fours. I mean, either of them could work. But I was like, if I count everything, it gives me like a consistent length. It can either be this or it can either be this. And what's the length? 17. So I'm like, okay, try to take 17 characters, try to pass into a MAC address. If it fails, try to take 14 characters, which is the length of the other one. And and try to pass it into a MAC address. And if it succeeds, return a MAC address for me. Because whatever logic is there, the MAC address, so this is from a crate called MAC address. Then that crate already has the implementation of matching a MAC address. So I was like, there's no need of me implementing this thing twice. After all, I'm still going to pass it eventually. So I was just like, let me just use it. And same thing too for identifiers. Remember the example that we gave at the beginning of DSLs, like the Cloudflare uses, is you can see something like if IP address, maybe like this field dot length is greater than 10. So that value, like something like maybe input.length, is like an identifier. So you can say check if an identifier, this particular value, so that this identifier is greater than 10. And so I'm passing that here. And generally, we know that most of the time in most languages, you don't start your variables. Variables are in this case are same thing as identifiers. You don't start them with like your integers or something. So what I'm doing here is I'm saying take an alphabet with a Unicode, right? You can take that or attempt to take an underscore, because variables can start with underscores. And so there's a function called pair, and pair is saying match on this and also match on the second one. So it will call this parser, this first parser, and also call the second parser, and then combine the results like together. So in the case where it starts with like an underscore at the beginning, it will concatenate the remaining. And why did I have to use a pair? It's because of I'm using like the alphanumeric Unicode one here. And the reason why I'm doing that is now I can now have numbers, but I don't want the first character to be a number. So the first value in a pair should exclude out numbers, and then subsequent characters that I encounter can have numbers. And Unicode, because I wanted people to like do things like maybe use emojis. If this store values are emojis, I know that's a really weird thing to like do. But Ross does it. I was like, oh yeah, sure, let's do it. Yeah. So something like this, you can create like pass identifiers. Now, but if you notice something about identifiers have full stops in them. If you look at DSL like the Cloudflare had, it had like something like inputs.length. This isn't going to handle the full stop. And so, but the thing is, we've built this basic piece, which you can combine. And what would I do? So the next thing I will do is say, pass an identifier and see if there's like a full stop in between, full stop followed by another identifier. So for example, that would mean if I had something like input.length, the first identifier that we pass would be input. And because of this preceded, I would get the dot length. And the advantage of this many zero is like I can continue calling that like recursively. So I can keep matching on dot length, dot size. That just assume it was input.length or size. Let's assume. And so what that does now is, if you look at this type here, we have first. The first is like the first part, and there's a remaining. So the remaining can be empty if the variable doesn't have a full stop in it. And it's just like a vector over like past input. And so what I just did was create like the first value, push it into like a vector, and go through the remaining and push it into the vector. You can also decide to use like a linked list, whatever the case might be for this. And so now I have all the fragments of the variables, the identifier that's being used. And I just wrap it into an identifier. An identifier is also a type that I created, which we'll see over at the end. Same for operators. So now we've talked about numbers, we talked about strings. For operators, there's this macro also still in the monkey lang crate, and it's really nice. Like anytime I see, I'm like, oh, this is really nice, because it's specific and it does exactly what it's doing. And what it's just saying is take this tag, like whatever identifier is being specified, match on this tag, and return the token specified. We'll look at an example. So let's assume we have this. We call the macro and we say create a function, a parser for me called and operator that matches on the ampersand, two ampersands, and if it passes successfully, the return type should be a logical operator, which is an enum that we created, and the variant should be and. So same thing too for OR, same thing too for XOR. So generally, this is just basically helping us to build all the other functions that are similar to strings, numbers that we have created. But yeah, so these for logical operators, and then how do we combine everything? So we have the alternate for each parser, the alt parser, and it says either match an AND operator. If it fails, go to OR. If it fails, go to XOR. And anyone that if it succeeds, if either of them succeeds, return a logical operator type. Yeah, same thing too for comparison operator, which was why we created the macros, because there are a lot of this. And so similar thing, try to create a parser function called equal operator, match on this input string. If it matches, return the equal variant for comparison operator of NU. And then bringing all of those functions that we created here into this place. And so we have a function, a parser that says lex comparison operators, and it says try to match an equal operator. If it fails, go to the next one. If it fails, go to the next one. Okay.
How would you deal with the precedence of different operators? Would you implement this right in here, or would you do this in a kind of, I wouldn't call it inference, but kind of logic extraction step based on your AST then? Or would you kind of put this logic in here?
Okay, that's actually a very good question. So personally for us, when we're implementing ours, we knew that we can implement operator precedence by how you arrange your parser generally. Some people would have like operator assign like tokens to values, and then based on that, or probably like operators to values, and based on that, so for example, you can give all the tokens that are on the same level a priority of 1, and some other tokens you can give them a priority of 2, and while you're passing, you can factor in all of those precedents that you've already like predefined. But that was for us, I felt like that was like an overkill. We just knew that we could, if we arrange our parser correctly, we can implement operator precedent. So we just went with that.
Thanks.
Yeah, you're welcome. Yeah, so that's comparison operators. So all these little parsers that we built. And so we built all of these necessary parsers that make up all the little modules to implement the filters, the Wireshark filters that we've been talking about. And so how do we combine all of this together? We need to understand, firstly, the structure of the DSL that we're trying to implement. So this is an example. It says frame.length if it's greater than 10, or frame.time if it's equals to this, or TCP.port is equals to this, or TCP.port is equals to this, or TCP.port is equals to this. Firstly, it means that we can have single operations, or we can have operations, multiple operations within one. But the way to think about it, just the same way when you're writing like context-free grammars, is to think about the little pieces and then identify how you can combine all these little pieces into one. So the little piece so that we can get started with is the single operation. And what's the structure of the single operation? It says we're expecting an identifier followed by a conditional operator followed by an operand. And the enum and an operand. An operand can either be a number or a string or a MAC address or whatever the case might be. But that's generally the structure. And then there is now the extra step, which is like the root of like the grammar that says you can have a single operation with one or more of this. And what does this do? It says it's either we have 0 or more of this, and with preceded by logical operator with a single operation. That means you can have that means this little part where you have the or TCP port equals to 443. That's like just one in this, but you can have multiple of that. But the requirement is you must first of all have a single operation. And so once we understand like this entire structure, how can we represent this like in Rust code? This is one way to represent it. The root, you have an operation and you can have extra operations. Extra operations can then be a vector of a logical operator with an operation. So similar to what we had here, we're just representing here. So since the vector, it can either be 0 or many. So we have this structure. Let's expand on this structure to see what all these types are. So we have the EST, which is here, and it says an operation. An operation can be, an operation, remember, has an identifier with a comparison operator with an operand, which is an operation. Now, what is, and then a logical operator, which we passed. Remember, a logical operator, we check if it matched the double ampersand and so on. So we have this enum called AND or XOR. What is operand? Operand is just, it just wraps a value, a concrete value. So it can either be a Boolean, integer, MAC address, string, or datetime. These are like where the primitives. And then we have like a comparison operator. I had a comparison operator. Just also to mention, there are obviously different ways to go about implementing this. Some people will decide to have a lexing stage, then a passing stage, then the execution stage. But like in this case, I was like, I don't really see the need to like implement like a lexer, like a complete like lexing stage where you lex everything and then you pass it. So, which was why I didn't have like one single element with tokens and all the tokens in the that is being used in the entire parser. But I just wanted to like mention that. And so we build all of these little functions. Then how do we combine it into a single operation? Remember, a single operation has, so we use the tuple. So the tuple, what tuple says is that it matches all the passers you pass in a sequential order. So remember, we have the lex identifier from parser that we already wrote. So it passes the identifier, and then we have this parser provided by num, which is multi-space 1. So what is multi-space 1? Obviously, if you had like your identifier and you concatenated it and you wrote a number subsequently after that, it's going to lead to ambiguity, or it will still be treated as the same identifier. So a language, the DSL will often have spaces in between this. So you want to pass that space, even though we don't necessarily need the space. So what we are saying here is check for one or more spaces after this identifier. And what this multi-space does, it handles things like new lines, spaces, carriage returns with new lines, all of those things. So it just eats up any space that it encounters, and then it now tries to pass a comparison operator. Remember, that's the next thing in a single operation. If it passes the comparison operator, there can be spaces. There should be spaces. Then that's what this next one is for. So it passes the spaces, and once that's passed the space, it passes the lex operand, which is the right-hand side of a single operation. And so if it passes successfully, the map function takes the result of the parser and passes it into this closure. Now let's look at the definition of a closure. A closure has an identifier, which is the return type of Lex identifier passer function. Then we have, I escaped this, but if we check the type that is here, it's a white space. I don't need a white space. The next thing is the operator, which was the result of the Lex comparison operator. And if you check the type from Ross Analyzer comparison operator, and then there's the next space, which I'm not interested in, so I skip it. And then we have the operand. And so if it passes successfully, we want to build our struct that we created and pass in those values and return it out of our pass operation function. So this is it for single operation. So I really like this because it's very easy to think about. Just the same way you think about how it's arranged, it's the same way you call all the functions. You need it to be called sequentially, you write it sequentially. So you've passed the single operation. Now what is left? It is the overall AST. Remember, the root contains a single operation with 0 or more operations, which we call the extra operations. So how would we pass that? So we set a tuple. What I like NOM is there's not a single way of doing things. There's a tuple here. I could decide to use a pair because I just have like only 2 functions, or I could decide to, but I really like the tuple function because most times I just think through if I think the first function that comes to my head is what I use. And so what I'm doing here is pass operation and attempt to pass 0 or more lexical operator with an operation. So which is why so this is like a passer. So remember there's a tuple passer. So what the tuple passer generally do is pass the operator, the logical operator, and pass an operation. And we are saying that keep passing as far as there is a logical operator and a pass operation. Continue passing that. And so if you check the output is firstly an operation. And there are extra operations, which is a vector of a tuple, a logical operator, and an operation. And how did we get that? Remember, firstly, this passes the tuple, the logical operator, and the pass operation, and we're saying 0 or more. So it keeps passing, and which is why this is a vector. The vector of tuples generally. And so if that passes successfully, we want to return the AST with extra operations. And if it fails, we want to return a pass error generic. So I just created this error type of generic just so that I don't talk so much about like errors and all of that, because that alone is another thing on its own. But this is just a generic error. Okay.
So, as far as I understand, you skip parsing the white spaces between operators here. Between the parser.
And that's actually very true.
Not important, just.
Yeah. But I mean, if you, I think this. Thank you so much for that. Like, probably, like, if you're writing tests for this, you would immediately like flag this, and you would know that there's a space that's missing there. And this is why I really like it because, like, for example, it encourages like the concept of like TDD. Like, you know how it functions. A parser that you're writing should work. You just immediately like spin up like input strings, call the parser, and then you keep calling parsers together until like that test case like really meets passes. So yeah, I think that's like one reason why I really like NOM. Yeah, you generally like catch this. Yeah, so the next thing we've built the AST now. We want to execute it. Remember, like you build the DSL, you pass it successfully, you want to execute it with domain-specific data. So for example, a user that is saying IP address, IP address dot maybe or input dot length is greater than 10, you need to get the value input from somewhere, obviously, and most of the time that input is specific to that user. So you want to be able to load that data into an environment that you can pass, that you can inject into your code for evaluation. So that way you have a code for evaluation that is independent of an environment. So why is that? Why should we do that? And so we can see this struct. It says an environment. An environment has a value called std. I don't think the best name to use. Then there are variables, and then there is a parent environment. Why do we have a parent environment? So for our own use case, we wanted to keep, there are certain things that are, there are certain functionalities in an environment that are shared across different users. Like, for example, maybe there are certain functions, like this, probably for our own case, we had like inbuilt functions that we had written that all users might be exposed to all users, like for example, mean, mode, the min, max, all of those kind of functions. Those functions should be shared across all environments for all users, but there should also still be that demarcation between what is shared between all users and what is specific to a user. But the thing was, there was, for example, like you have all these functions, you have all these preloaded data, and so what we did was we initialized the environment. We have like a global environment, which is the parent environment. And so any new environment that we want to create, so for each request, we kind of like build a new environment, which is just like building a struct, but like takes like an atomic reference to the parent environment. Atomic reference to the parent environment. I have this other environment for it. So what that means is users can, although there are certain things users can't override, but if a user is making use of, let's say, a variable, says maybe there's a variable, we will first of all check the user-defined environment if that value exists, and if it doesn't exist, we keep going down until we reach like the parent environment. So, for example, if someone were to use an inbuilt function that we had written, obviously it wouldn't be on the variables, it wouldn't be on the std specific to like a user. We would find it like in the parent environment. So, environment abstracts all of those things. Environment abstract all of those things. So these are the functions we have. So we made a way for whether you want to create an environment with the global environment, or you want to create an environment without a parent environment. A good example for this is like testing that you want to be able to write tests to ensure that users don't call things they don't want to call. So like these kind of functions are kind of like very helpful for us. Yeah, you might be wondering what identifiers map is. Identifiers map is just generally like a name of a value. Like, so for example, it can be the mean function. So it can be mean, and then what is the data kind? The data kind can be different types of data. It can be either a function, or it can be like a variable, or whatever the case might be. But it's just like a basic structure that stores like types and environments. It's pretty basic. And so we have this environment then that contains data specific to a user's domain. To the user we're trying to evaluate that formula for, right? We have this environment, we have the AST, then how do we evaluate it with that user's specific data? That's where evaluation comes in. Obviously, this is just a pretty basic implementation. The way we went around it was pretty much similar to this. So you remember you have an operation. You have an operation, a single operation in this case, and it has this function called eval, and it takes in an environment. So you want to be able to evaluate this single operation with this environment that you injected into it, and that way we can write tests on operations where we can stop the environment. So that's like why we had something like this. So you can create mock data in your environment and call eval on an operation to see if it returns the expected value that you want. And so remember I said environment just basically has like some functions, like one of the functions is get. And what it does is like we are saying, remember an operation has an identifier, an operand, so an identifier, an operator, and an operand. So what we are saying is check in the environment. Does this identifier exist? Does it have a value there? Either it was predefined from the user-specific environment or from the global environment, if it was initialized with a global environment. And if you find that data, if you find that data, we have the concrete type, which is the left-hand side, then we want to match on the operand. We want to match on the operand with the operator still within this operation. Remember, operation is a struct that has 3 types. And so we pass in the left, we pass in the right. Obviously, this function could have been implemented in a better way, but yeah, we pass in the left, we pass in the right, and it can get the operation inside, or we could have just made this function just a static function. But generally, the concept is it passes in the left, passes in the right, and it has like the operand, the operator. And if it fails, we return unknown identifier. So these are like a sneak peek of how we would go about errors. Obviously, there will be more. There are better abstractions you can do to return, even when it tries to evaluate here, you can return span information and all of that. But a stripped down version is if you can't find this identifier in any of the environments, either the user specific data in the global environment, we want to return unknown identifier. Most likely, the user is using a value. Is on the left hand side, specify the value we don't support. And also remember there's an operation and then there's the EST. So an EST, remember, comprises of a single operation with zero or more extra operations. So what we are doing is pass the single operation first and inject the runtime. Sorry, this is meant to be like an environment. Inject the environment into it. And then so it evaluates to a Boolean value. Remember if we check the definition of this eval, it returns like a Boolean value. So we evaluate one single operation, and then we say for subsequent operations, we want to proceed to evaluate it. And so how does that work? So we're just folding where the initial value is the single operation we've evaluated. And so we are going through all the subsequent operations with the operator and the current value we want to evaluate on. And so we say the current value from the extra operations, we want to evaluate it with this environment, still for that same user, because it's still within the same context generally. And if it succeeds, we get the right-hand value, which is a Boolean. And then remember there are like conditions that says either this or this and this. And so we match on that operator which is like the first value in that tuple of extra operations. So if it's and, we say the left and the right. So if it's a true and a true, we return the true. And so on. And we keep doing this. Okay.
So if the left evaluates the true, do you evaluate the right hand side at all?
Yes.
You evaluate both of them?
Yes. And the reason why we do that, so if you can walk back a bit. So an example we had over here. For example, it says if the TCP port is equals to 80. Yeah, that's true. Yeah. If the TCP port evaluates to 80, if it's a true, we don't actually need to continue. That's very correct. So that's actually work. Yeah.
It's not a bug, it's a performance optimization.
Yeah.
Unless there are side effects.
Yeah. So yeah, that's very true. So if it returns a true, I mean, obviously this will need to like be tweaked. I'd say if it returns a true, there's no need of us returning a true. And the reason is because it's pretty much a flat structure operation. But like in cases where there were things like brackets, and all of those kind of cases, those might be cases where you might decide if you want to proceed or not. I adapted this from a code that uses like brackets and all of that. So this evaluation and so errors. So I mean, most of what we did here, we didn't really talk extensively about errors, but I just wanted to like talk about it, about like just a stripped down version of how we represented errors. And I really like it because I feel like it captured like a lot of cases where we needed. So first of all, we have pass errors. So if it fails to pass, so it contains like the kind of the error, it contains the span information. Spans are just like columns and so on and so forth. And tokens is just like the source input at the point where the error failed. And so basically one kind is of error kind is we expected this type, or we expected any of this type, or we came across a type that was unexpected. So for example, if you're writing Rust, you might see scenarios where it might tell you that maybe probably you did, let's say, a value that holds a boolean equals to a string. Rust will tell you probably something like this type. It expected like a boolean here, or it expected any of these types here. So a structure like this kind of like encapsulates like that kind of information. And so that's when we're building like span information, especially like runtime, we could then decide, okay, what type of error should we return here? Should it be like maybe we expected like any of these types? So for example, one use case would be if we're passing different variations of numbers, and we can say we expected any of I32, U32, I64. So that's when like this second variant will come in. And so for like runtime errors, pretty much the same. Undefined identifiers, we expected a boolean, we expected a number, we expected a string. All of this you can still encapsulate it into, you can still adapt like this same structure. It just really depends on what exactly you want. And then you have like this root error type that has like all the different types of errors that you have. And generally this was like what we did. And this is like the end of like this talk, but I think I should just mention briefly after all of these things. So you might remember at the beginning we talked about like portability and all of that. One good use case, when you've implemented this on your backend, you could decide to compile your entire language, DSL, to a WASI module, which you can call in NPM. For our own case, when we compiled our own, even without release mode, it was at 160 KB, including the parser, the lexer, the parser, the runtime, the environment, all of these things was around like 160 KB, even without like release mode. Obviously, we didn't go with that, and one use case of probably going with like WebAssembly, compiling like your DSL to WebAssembly is your front end no longer needs to make calls to the backend to evaluate user inputs, or you don't need to set up things like language servers and all of those things. So because the module is on the front end, you could have things like on change. So if the text input changes, you want to call the function exposed through WebAssembly to attempt to pass and get span information, and then you can present that in real time to like the users. Or you can have like a naive implementation of attempting to pass the entire like code at once and show all the different places where there are syntax errors and all of that. So good use case because it's happening on the user's browser. You can present all of that to the user without the front end making requests to like the back end. But I just wanted to like mention that. But yeah, generally that brings me to the end of this talk. It was pretty long.
I have a question.
Yeah.
Regarding on your last slide, you had these error enums.
how detailed you get access to the like places in the input stream, like in order to have meaningful error message. For instance, if it's a DSL that you parse, right, you may want to instruct the user that at this very place, this token is not accepted, but you would suggest him with the accepted tokens there, right? How well you can get access to this data?
Yeah. So there are a couple of things I didn't mention. So firstly, what we did, we had 3 stages, the Lexa. And so what happened was when we passed each of the Lexa, so for example, we passed a truth. So that token, we wrap the token in a type that contains a span.
Okay.
So each of those different independent tokens that we pass, we store the beginning, we store the end, we store the line information, beginning line information, end line information. And so we have all these little tokens, and when we come to the passing stage, we have that information.
But what if something on the lexing stage already happens because a token, for instance, imagine the word matches, right? That you would expect, but it is not spelled right. So it is, maybe there's a typo in it. The lexer would fail at this very point because it would expect the literal matches, for example, right?
Yeah.
So then you would not have the possibility to wrap the token because there's no token to wrap, right?
Yeah.
But do you still get like the place where in the DSL you would be, and what would be the accepted tokens at its very place where it failed?
I didn't include that here, but because there was no Lexa stage, but we had like Lexa errors. And so, for example, in a scenario where we're unable to pass maybe like matches and we've tried everything and we can't pass it successfully, we would say unrecognized identifier, unrecognized value, which generally in languages like Python or in most languages you would get like unexpected identifiers. Most of the time, those are Lexa errors because you can't give more concrete.
Yeah. That's I mean, that's one of the like downsides of those generators, because you don't really get the data that you need to give really meaningful suggestions.
Yeah, true.
But yeah, cool. Thanks.
Usually for editors, if you have an editor or something like this, you don't want to stop parsing and then you usually want to parse as far as you can get, even if you encounter errors.
Yeah.
So I suppose I'm not sure how you implement it, but I suppose the error types would need to be collected over all of the source code that you write and with the expected conditions and so on. So I suppose I'm not sure how you said that you've implemented in one of your products. Did you have to implement it like this so that you parse as far as you can and then report all the errors that you find and not stopping at the first error? How complicated is that?
Yeah. Okay. So, firstly, we one of the things one of the considerations we're going with was export the language as WASM, and the major reason was because we wanted to pass as far as we can go, and so that the front end can show all of those errors at once. What is the naive implementation to implement it? What we did was attempt to pass. Once you encounter an error, stop passing them, get the error, and attempt to pass further. Like that's the naive implementation. Attempt to pass further from after when you stopped passing. So for example, if you were passing an if expression and it doesn't have maybe you have if closing braces, and then you have the open bracket, and probably you had like a curly braces instead. You would flag an error there, so we would say something like expected either an identifier, expected any of identifier or Boolean expression or integer or whatever the case might be, and then we continue passing subsequently from after that. That's like pretty naive, but like that way we can pass everything and like get like errors that that more kind of errors that could have occurred like subsequently down the line. And so we just combine all of that and just return it.
If you already know what you would have expected, you could just assume it's one of these tokens and then keep your context and keep going from there.
Exactly, because you need
That's
context
true.
to continue parsing.
Yeah,
Yes,
that's
but the hard part is figuring out what could
Yeah.
be coming next and having that data available at any possible
So
moment.
if you're in an if and you encounter an else, it's not valid on its own, the else. So you need to know that you were in an if, for example. So you need this context to parse.
Yeah, sure. I mean, that's actually a great idea. But I mean, I feel there'll still be other issues like what if they're not closing braces? There are still other things. I feel like that's a lot of research to like do.
I think there are books written about
Yeah.
this error recovery from parsing. Rust Analyzer has a blog post about how Rust Analyzer does it. So,
I mean, you can even simulate it with the possibility tokens that can occur there. And in parallel, you would like assume this would be there, and then continue parsing and see how this flies, and then
but then you run the possibility that you get many useless errors.
Yeah,
Like in C++,
exactly.
if you forget a semicolon, then everything after that just fails to pass.
might continue without the state actually after lexing. It might also be very like useless follow-up errors.
It's definitely not an easy problem. So.
I like the way that three-sitter does it. So it would force the parser if there's one token is wrong, that there are generally two possibilities that it could continue parsing by. So it continues both ways and counts how many errors the two parsers get, and this counts how many errors. And then the other one is probably correct. Three-sitter is interesting, but someone should like port it all to Rust because now it's a mess. It's made in C, C++, JavaScript, and Rust.
Java is just the front end part, right? It's just
So-
the functions, grammar part.
Regardless of the languages in Trisita. Thank you, Tox. Thank you for your talk. Thank you. Yeah. If there are any questions, then now's the time.
Let me see if there's something.
Another one. Some time ago, I did a grammar, and which was like this yak thing, like the old way to do grammars and Lexia. And for me, this was like the moment was like quite crazy because I write this grammar and then it generates code and it creates me an editor and it creates me automatically syntax highlighting and everything for free basically. And I think that those two, I don't know, so my question is maybe, do you see a way how to combine those two worlds? Because I think both sides have their problems and advantages. I think, so what I researched right now was that there's no way to have an editor or syntax highlighting for your DSL automatically. This would be awesome, like if you were to write something in LOM and then export a grammar, this would be kind of cool. It looks like it would maybe be possible, but
Yeah, that's very true. So I was actually I was listening to talk recently, and it was something related to that. I can't remember exactly where. I think he's currently at Elastic, and they like built this kind of like similar to none but different, where you define like a grammar and it generates like the corresponding like VS Code, IntelliSense, and all of those things for you. I can't remember exactly the name of the project, but if I remember, I would.
I think what is pretty famous and used everywhere is Antler.
Yeah.
You can define your grammar and then you have lots of generators. You can generate like then everything for Java, JavaScript, whatever you want. You get the visitors for the AST. And I think other tools they build on top to bring you even more like, I don't know, maybe syntax highlighting would be possible.
maybe so. I think it's different use cases where you would use the both. I mean, probably if you use Android, I would just guess the resin file would be 5 megabytes. I don't know, or it might be huge. And NOM is maybe more for more sophisticated projects where you want the maximum performance, maybe. I don't know.
I think the Enter generated code, there is a Rust binding to it. I don't know if it's really binding or like a re-implementation of the runtime. The code that it generates is like not too awful, but really nicely.
Maybe the runtime, yeah, I don't know.
And then you can like essentially compile it also down to resin. So it's really not huge. You can read it.
So yeah, I'm just trying to understand like where do I use what.